Welcome to this chapter. This is about diagnostics in nuclear medicine. Just a short introduction to the basics. What is the goal of diagnostics? We would like to image biological functions in a body. That is the subject of nuclear medicine. Please note this very important difference. When you say radiology, radiology uses external radiation sources, X-rays. This is the Bremsstrahlung Distanztwister type of X-rays to obtain information on the anatomical structure of the body. Sometimes this is a very simple imaging, sometimes it is a little bit more complicated, which is called CT. Later we will have some time to explain this. Nuclear medicine is much more developed, much more advanced technique. It is looking for a given biochemical process with the help of incorporated radionuclides carried by the biomolecule, and that's the point, biomolecule, that makes it biologically selective. What we can use is what type of radiation, what type of emitters, only gamma emitters, because only gamma rays can be transmitted through the human body with dimensions of several tens of centimeters. You may remember that I mentioned for gamma rays almost everything is transparent, just like the human body. However, taking into account these dimensions of several tens of centimeters of relatively light material, we have a recommended gamma energy range from 100 kV to 300 kV. Please also note that if gamma rays can easily pass through the body, it means a low level of absorption, therefore a very low dose. It is important for us. And the higher the gamma energy, the lower is the absorption and attenuation rate. Oh yes, this is not so simple to understand as in the case for alpha radiation and beta radiation, because you may remember the interaction between gamma and matter is a little bit more complicated. But this is the final conclusion. Interestingly, the same. So the higher is the energy of the gamma radiation, the lower is the absorption. We will see later the consequence of it. The consequence is actually this recommendation for the optimal energy range, which here it is a question, but I would like to explain you why we have it. As I said, if we have a low energy gamma rays, then they are easily absorbed in a body. So, since the human body contains mostly light elements, it is for sure that any gamma ray can be easily leave the human body, and the gamma radiation, which comes from any part of our body, would reach the detector. So, as I said, if the energy is higher, then the absorption in the body is also lower. Therefore, we are interested to use large energy, high energy for gamma rays, so that the dose for the patient would be lower. However, we have a problem that the same tendency is valid for the detector crystal. If the energy is too high, then the absorption in the crystal will be too low. So therefore, we are not interested to have any high energy gamma, because we would like the detector to absorb it, because that means the detection. So for this reason, we have an optimal range. Of course, as I said, our body is relatively light. We are composed of hydrogen, oxygen, carbon, nitrogen, phosphorus, calcium, some other elements, relatively light material. However, in order to increase the detection efficiency for the detector, we select a detector crystal composed of heavy elements. Sometimes it contains iodine, for example, and mostly the photoelectric effect is responsible for this difference between the absorption in the body and the absorption in the crystal. So there is a strong absorption in the detector crystal. So we are not interested in having too low energy gamma rays. Why? As I said, the optimal range is from 100 kV to 300 kV. If the energy is too low, there would be a self-absorption already in the body. For example, if you have a 10 kilo electron volt gamma radiation, it would be absorbed in 1 centimeter of water. So it would not leave your body. The doctor would not have any information coming from your body. If the energy is too high, then this gamma ray would not be absorbed in the crystal. So finally, I think we understand why we have an optimum range for the gamma energies. So if nature offers us the proper isotopes, we should select gamma energies from this range, from 100 kilo electron volt to 300 kilo electron volts. In this page, I would like to show you some examples of isotopes used in diagnostics in nuclear medicine. Only 4 isotopes you can see here. The first one is technetium-99m. What is important for this isotope from the point of view of diagnosis? M means that this is a metastable nuclide. It means this is a pure gamma emitter. So there is no beta emission, because if you have beta emission, then the beta particles would destroy the issue in a millimeter range around the technetium isotope. However, in this case, there is no particle emission. The same thing is true for indium-111, iodine-123, and xenon-127. EC means that electron capture. When electron capture occurs as a radioactive decay, this is one type of the beta decay you may remember, then an electron is captured from the innermost shell of the atom. Then you have a vacancy on the K shell. When this vacancy is filled from another electron shell, then you have a characteristic X-ray emitted. This X-ray may be detected, however, normally the energy of this X-ray is very low, so it's not really good for medical purpose. However, after this electron capture, you have a new nuclide, and this new nuclide is radioactive, and in the sense that it is mostly in an excited state. So if it has gamma emissions, like in this case 172 kilo electron volt and 247 kilo electron volt emissions, and also you see similar emissions for the other 2 isotopes. So when you have electron capture, the point is that you have no particle emission. So if you use the isotope for diagnostic purpose, then you don't introduce an isotope which after the radioactive decay would destroy the neighboring tissue. It just emits a gamma which has a relatively low harm, a low-level harm to the tissue. You see, the energies are really more or less in the 100 and 300 kilo electron volt range. Of course, you depend on nature. If nature offers this, then you have to accept it. The half-lives are typically relatively low, at least for the first 3 isotopes. For xenon, it's a little bit longer, but what can you do? This is mostly used for lung functioning tests. Technetium is the most important one. As you see, 85% of all the nuclear medicine applications is done with technetium-99m. It is quite a funny coincidence that technetium-99 is the element. Technetium is the element which does not exist in nature, because it has only radioactive isotopes, and still this technetium-99m isotope is the best for nuclear medicine. Indium-111 is a tumor marker. We will see later an example how it works. Iodine-123 is similar, has a similar application to that of technetium-99m. And as I said, xenon-127 is mostly used for lung functioning. Thank you very much for your attention.